Welcome to the Explainer. Okay, let's dive right into this. Today, we're exploring the fascinating, foundational world of chemistry, pulling directly from an awesome masterclass lesson by Hafsa Unjum. We're talking about acids and bases. But hey, we aren't just going to sit here and memorize formulas, right? Instead, we're going to look at the invisible rules that govern everything from the sour zing of your morning orange juice to the heavy industrial reactions that literally shape our modern world. Let's get started.
Here's our mental roadmap for today. First up, the everyday traits of acids and bases. Second, their theoretical definitions. Third, chemical reactions of acids. And finally, the chemical reactions of bases.
Section 1. Traits of acids and bases. Before we get into all the complex molecular exchanges, let's actually ground this chemistry in the physical, everyday sensations that you can experience and relate to. Acids? Well, they have some pretty distinct, sometimes aggressive physical personalities. They're famously sour, think of the citric acid in a lemon, and they can actually be genuinely painful to the touch. We generally divide these into powerful mineral acids like hydrochloric acid or HCl, and organic acids like acetic or citric acid. Bases, on the flip side, are a completely different experience. They're bitter to taste and noticeably slippery to the touch. It's a lot like holding a wet bar of strong soap. Examples here range from basic oxides to water-soluble alkalis like sodium hydroxide or NaOH.
Section 2. Defining acids and bases.
Now, knowing how they taste or feel is great, but chemistry is really about the why, isn't it? Let's talk about the theoretical detective work scientists use to figure out the invisible rules behind these exact traits. The first theoretical lens we look through is the Arrhenius concept. This is a very specific foundational definition. It essentially states that an acid is a substance that donates hydrogen ions, that's H+, when it's mixed into an aqueous medium, which, is really just a fancy way of saying water. For instance, if you drop HCl into water, boom, it releases those H+ ions. A base, under this exact same lens, is a substance that donates hydroxide ions, or OH-, in that same watery environment. Sodium hydroxide doing this is a textbook example.
But as chemistry evolved, scientists realized they needed a broader definition, one that wasn't strictly tied to just water. Enter the Laurie-Bronsted concept. This definition beautifully expands our understanding by focusing entirely on the vital exchange of protons. Here, an acid is quite simply a proton donor. And when it donates that proton, what's left behind is called a conjugate base. Conversely, a base is a proton acceptor. When it accepts that new proton, it transforms into a conjugate acid. Honestly, it's like an elegant microscopic game of catch.
Let's look at exactly how this works in practice. Imagine we have ammonia, NH3, and hydrochloric acid, HCl. In step 1, our acid, the HCl, steps up as the proton donor. It throws the proton. In step 2, our base, the ammonia, acts as the proton acceptor. It catches the proton. And the result in step 3? Well, the ammonia becomes NH4+, which is our newly formed conjugate acid, and the HCl, having lost its proton, becomes Cl-, which is our new conjugate base.
Now, what's really interesting about this next concept is that it's the final and broadest theoretical lens, the Lewis concept. Instead of focusing on protons, Lewis shifted the spotlight entirely over to electrons. According to this framework, a Lewis base is an electron-paired donor. It's what we call nucleophilic. Think of it as being wildly electron-rich, just absolutely bursting with a pair of electrons ready to be shared to form a new bond. Things like ammonia, water, and chloride ions perfectly fit this description, mostly because they have those extra electron pairs just sitting there, waiting for a partner.
Section 3. Chemical reactions of acids. Now that we understand the rules of the game, the protons, the electrons, it's time for some practical application. Imagine stepping into the laboratory right now. We're going to look at exactly how acids interact with the physical world around them once we start actually mixing things together in the test tubes.
Grounding these abstract equations in reality, let's look at some real interactions. When an active metal meets an acid, like say zinc reacting with sulfuric acid, a pretty remarkable transformation happens. The acid aggressively breaks the metal down, creating zinc sulfate and releasing hydrogen gas. Now, what happens if we use a carbonate instead? Well, if we take calcium carbonate and react it with hydrochloric acid, the results are entirely different. We get calcium chloride, sure, but we also yield water and carbon dioxide gas, CO2. The acid literally dismantles the structure to release these gases.
So, the crucial point here is how acids interact with other highly reactive compounds. Take neutralization, for example. When our acid, HCl, meets a strong base, like NaOH, they completely neutralize each other in this grand chemical showdown.
leaving behind just harmless salt, NaCl, and water. But acids can also aggressively dismantle other compounds. React an acid with a sulfite, like calcium sulfite, and you produce sulfur dioxide gas, SO2. React an acid with a sulfide, like iron sulfide, and you generate hydrogen sulfide gas, H2S. Acids truly are the master transformers of the chemical world.
Section 4. Chemical reactions of bases.
We've seen how acids tear things down and force transformations. Now, let's flip the script and shift our focus to the other side of the chemical coin. Keep that structured, analytical mindset going as we observe these basic compounds go into work in our next set of experiments.
And this brilliantly illustrates the sheer power of a basic reaction. When you take a base, like our old friend sodium hydroxide, and introduce it to an ammonium salt, like ammonium chloride, well, you get a very specific, highly volatile result. The products are salt and water, yes, but the absolute star of the show here is the rapid release of ammonia gas, NH3. It is a classic, pungent reaction that immediately proves the base is actively tearing that ammonium salt apart.
Finally, let's quickly detail how strong bases like sodium hydroxide react with different metal compounds. Honestly, they act almost like chemical swap meets. If NaOH reacts with zinc chloride, it swaps out to form zinc hydroxide. React it with iron chloride, and you get iron hydroxide. React it with lead nitrate, you yield lead hydroxide. In every single case, the base forces a structural exchange, forming completely new, distinct chemical products that often drop right out of the solution as solid precipitates.
As we wrap up this explainer, I want you to really think about this. We started with the simple, macroscopic experience of a sour taste or a slippery touch, and we journeyed all the way down to the invisible, fundamental exchange of protons and electron pairs. Understanding acids and bases isn't just about balancing equations on a chalkboard, it's about understanding the silent, microscopic architecture of the world around us. So, from the sour taste of a lemon to the invisible exchange of protons and electrons, how did these microscopic rules continue to shape every single physical sensation you experience? Keep that in mind next time you bite into a piece of citrus or wash your hands. Thanks for joining me on The Explainer, and keep learning.